Hello, YouTube. Today, I'm going to take the pen out of my mouth so you can hear me. Today, we're going to talk about how to do a couple of problems related to mechanical energy that, in particular, will hopefully make it so that you're able to solve similar problems. These are pretty much going to be exactly book problems that are assigned for homework, but I'm going to take away the numbers is the only real difference, and I'm going to not necessarily say the exact same I guess just not exactly give the same problems as the ones from the book, but enough that the sort of key twists are in there. So, starting off with a problem that involves a block going down a hill into a loop-de-loop. And sort of a classic physics problem is to say we've got this block, we drop it from a height h to a loop of radius r, and the classic question I'm actually going to put as part B, which is, what is the lowest h in terms of r such that the block does not fall? And the part A that goes with this, in my mind, because it's going to be one of the sort of setting up all the setup, is what is the normal force on the block? And this is going to be in terms of a bunch of stuff, but just to get the setup and good to go, that's sort of the first thing I want to be thinking about. So, why would there be a lowest h? Why are we caring about the normal force? What's going on for this situation? Let's just kind of start there. Well, for me, looking at this problem, one of the first big things I see is that there's two different locations, and that those two different locations are going to have an object that's moving at them, and that the stuff between those two different locations is kind of weird and confusing. There's a lot going on. There's the loop-de-loop. There's the hill. I don't know anything about angles. So I can't really use forces, and I can't really use kinematics, but I can use energy because there's two different locations for one object, and energy lends itself great to that. So the second thing I see is that there's a circle. So first off, I'm thinking about energy. And if I'm thinking about energy, then we're going to have location 1, and we're going to have location 2. And the energy at location 1 is going to be equal to the energy at location 2. So in particular for this one, we're going to have mgh. And if it's, this is actually, when dropped, which will matter. So at this first location, it's not moving, so there's no kinetic energy, so plus 0. And that's going to need to be equal to the mechanical energy at the end, which is going to be mgh2, more on that in a sec, plus 1/2 mv2 squared. So I'm setting up that my potential energy at my first place, which has just a height of h, or h1, which I would then sub for h, needs to equal the potential energy at my second place, which is mgh2, which I'll have to think of some geometry for later, plus 1/2 mv2 squared. My second thing that I can think about is that this is going in a circle. So because it's going in a circle, I know that the net centripetal force is going to need to be equal to mv squared over r. And for me, this is actually kind of relevant because, and I can see some relationship between these two things, because there's a v squared in both of those equations. So if I'm trying to figure out what things are using heights instead of those velocities, I can relate the velocity to the height using energy and then bring that over to the circles part of thing. Well, now I need to think about what the centripetal force would be. So at the top, our block looks like this. And there's sort of two forces going down on it. There's mg and there's Fn. At the bottom, we have a force going up on it, and we have a force going down on it. And one of the big things about this is that, like, our centripetal force is going to be whatever the net force is specifically directed towards the center. But that's not necessarily just going to be one of these. And it's actually going to be such that there's some stuff fighting against it in one case, and there's two forces working together in another. Because at the top, the normal force and the gravity both work together to pull it in towards the middle. And at the bottom, the normal force goes up to sort of help bring it up towards the top. There's a second thing here, which is that this isn't traveling at a constant velocity. This is the maximum velocity. This is the minimum velocity. So, in particular, if it's going to fall off, the top is going to be the place where it'll fall off first, not because it's getting pushed down the most directly, but more directly because the slower it goes, the less centripetal force you need. And we'll get to that when we start with part B, but for now that's just a thing to be kicking around in the back of your head. So specifically, if it's going in a circle, and there's some centripetal force, and I should have specified this at the top. And we're trying to find the normal force at the top, we have to set up our equation at the top. Fn minus mg, although both of them should be plus because they're both going centripetally, so they're both going towards the center, so the combination of the two of them needs to equal mv squared over r. Okay, great. So at this point, h is pretty much a given. I do need to find a way to represent h2, which, if I look at my circle, there's one r stacked on top of another r, giving us 2r. So h2 is equal to 2 times r. And now, I can solve for v in terms of h and r, which are both things that are sort of given in the diagram of the problem at least. And using mg, I can relate those to my normal force. So in particular, I've got mgh equals 2mgr plus 1/2 mv squared, where v is the velocity at the second location. If I subtract 2mgr from both sides, that'll give me that mgh minus 2mgr equals 1/2 mv squared. And I could cancel out the mass here, but I'm actually going to hold off on that for reasons that'll hopefully become clear in a sec. You could cancel out the mass and you would totally get the right answer and it wouldn't be a problem. And so we've got our 2. I am going to distribute the 2. So this becomes a 2 mgr, and this becomes h, and this becomes a 4 mgr. So from there, what's neat about this is that mv squared here and mv squared here are now a substitution we can make. You could divide each side by the m to get rid of it, but it would come right back in and you'd have to redistribute as soon as you put in that mv squared right there. So doing that out, what we can get is, so if we call this one equation 3, and this one equation 2, and this one equation 1, we can plug 3 into 2. And when we do that, we'll wind up with 2mgh minus 4mgr divided by r is equal to our normal force plus mg. So, from there, if we subtract off mg from both sides, we're good to go. Minus mg, and there's our normal force. I'm not going to put too much time into that because of a thing that'll happen soon. So let's start thinking about part B. In particular, why would there be a minimum height that we could drop this thing from? Well, hopefully it makes sense that if you drop it from below the top of the loop, it'll only go back up to the same height because it doesn't have enough mechanical energy to get any higher than that. Going higher than that would require more potential than it started with, and if it started with all potential, no kinetic, because we're dropping it, then it won't be able to go higher because it just doesn't have enough total energy to do that. So then the question becomes, well, why can't we just drop it from a height of 2r? And the problem is that if we do try to drop it from a height of 2r, it'll try to get up to this height, but as it does, it won't be going fast enough. And when it reaches the top of the loop, gravity will be pulling it down faster than there is loop. And the thing will actually wind up taking a tighter orbit because the centripetal force on it is too big for it to go in that wide of a circle for the velocity it's at. And it'll fall off the loop and not be in contact anymore. But if it goes fast enough, like faster, then it'll be going so fast that it'll be trying to shoot through the top of the loop. And when that happens, it'll make it through the loop because it'll constantly be pushing against the loop as it goes, trying to go into a wider circle, but being unable to do so because the loop is pushing against it. Now, the slower it goes, the less centripetal force it needs. And the greater a chance that the centripetal force it has will be too big for it to have a small enough centripetal force to go in that wide of a circle. So at a minimum velocity, when we are going slow enough, our normal force will get progressively smaller as we go at every point along the way. And eventually, our normal force at the top will just barely be 0. And at that point, when we just barely reach the top, we'll just barely have the box such that it's not actually getting pushed by the ceiling. And I didn't highlight this enough. The box is on the bottom of the loop-de-loop, and so because the box is on the bottom of the loop-de-loop, the ceiling pushes it down because it's pushing up against the ceiling, because that's the way they're touching. So what we can say is specifically at the minimum velocity, our normal force is 0. And that's super useful because this equation gets so much easier if that's true. Taking a sec to rewrite it. That's our answer to A. Taking a sec to rewrite it, we'll get that mg, and I'm going to bring the mg back over here, equals 2mgh minus 4mg r all over r. And real quick, we can just say, well, there's an mg in all of these terms. And if I go ahead and distribute this r, that one's gone, and this one is h over r. So what we'll get is that 1 is equal to 2h over r minus 4. And I just have to add 4 to both sides. And that gives me that 5 is equal to 2h over r. Multiply each side by r, divide each side by 2, multiply each side by r, divide each side by 2, and we'll get that the height for the minimum is equal to 5/2 of r. So just over 2r by about half of r. And that'll be the height at which it doesn't fall off the loop. If we drop it from any higher than that, it should make it all the way around the loop with no problems. If we drop it from any lower than that, it'll come off of contact with the loop at some point, possibly re-landing on the loop and finishing its journey, depending on where it comes off the loop. Cool. So that's pretty much the wrap on that one. You basically want to think about how, like, okay, well, the bottom is going to need the most force pushing up because not only is it going the fastest, so it needs the most centripetal force, but that'll actually also be the point when gravity's fighting against it. So just mathematically, you'll get way, 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 way more force on the object from the loop at the bottom than you will at the top. And that progressively changes as you go, getting bigger towards the top bigger towards the bottom and smaller towards the top. I think that's a pretty good primer on that stuff, and from there you should be good to go in figuring out the rest. I do want to talk about the, to me, infamous problem 34 from the book, and how you do the stuff with the hills. So this is another one where something is coming off of another thing. If we have a semicircular hill of radius r, and we pop a block on it, at what height will it slide off in terms of r? And something that I'm going to do real quick is label a bunch of stuff that I'm going to use temporarily, but will not use later on. So in particular, h is equal to r times the sine of theta, and that will come up eventually. And secondarily from that, we've got this height, which is r minus h, which you can use as a shortcut or you cannot use. And then we've got this, which via the Pythagorean theorem is r minus h, both of which squared, square rooted. Okay, so geometry junk out of the way. Let's start thinking about concepts again. Well, once again, we've got a thing going in a circle that's going to fall off a thing, and it's going to fall a distance to do it. So I'm going to start using energy. I'm going to start using circles. One thing to be aware of here is that for this one, instead of having a minimum speed because it's going to have too much force going to the middle, this one's going to have a maximum speed because it's not going to have enough force going towards the middle. So let's start drawing our free body diagram and thinking about this object when it's at this magical height where it falls. So at this point, I'm going to rotate it. There's going to be a few different forces. We're going to have mg going straight down. We're going to have Fn going up, and that's it. If there's friction, this problem changes because, oh god, yeah, friction's going to do work and it's going to be a nightmare. So we're not going to have friction for this one. I need to break this up into components. We're going to have mg times the cosine of theta. Sine of theta. Sorry, almost got my hills backwards. And mg times the cosine of theta. In particular, this one is always tangent to the circle, and these ones are the radial forces. Our net radial force needs to be centripetal, or this thing won't go in a circle. And so what that means is the net force on this thing needs to be directed like that. In particular, that means that if I take this force, which is centripetal, and this force, which is centrifugal, going away from the center, that if I take mg cosine theta, which I'm going to make positive because it's going the correct direction to go to a circle, minus Fn, which I'm going to leave as minus because it's the opposite direction as it would need to go in a circle, will need to equal mv squared over r. Now if I'm looking at this, I can always have there be less force. I can always make normal force be bigger. And if normal force is bigger, then while this thing is going slow enough, it can stop it from going into a tighter orb circle by having too much force and going towards the center, which is the middle of the hill. If I make the thing go faster and faster and faster and faster, then it'll need progressively less force as it goes. And so Fn will need to get smaller because it'll need more force as it goes. Because Fn is taking away force, Fn will need to get smaller to get the force to be bigger. But there's a problem. Fn will get progressively smaller as we go. And if Fn gets progressively smaller as we go, then eventually it'll get smaller and smaller and smaller till it's 0. And it can't go negative, so it can't pull into the hill. So this thing will eventually fall off the hill if it's a complete semicircle and there's no friction. So that's our main condition here. So once again, but for very different reasons, our normal force is 0 at our maximum velocity instead of our minimum velocity. Okay, well now what? Well, if we... Sorry, I thought of a easier way to set up the geometry that I'm not going to do because I know that the other way works. So this is our circles thing. We also can use energy because we don't want this unfriendly v squared hanging around. If we take the energy that we have at the top, which is going to be mgr, if it's not moving, that's plus no kinetic, that'll need to equal mgh plus 1/2 mv squared. And we'll wind up with something pretty similar to last time, minus mgh, but this time we'll have a sort of flopping of the r's and the h's, and some different ratios indeed. So we'll have mgr minus mgh equals 1/2 mv squared. And now what we can do is, once again, after bringing the 2 over, sub in for mv squared over there. And when we do that, what we'll wind up with is, and again, because this is 0, I don't really have to care about it anymore. Mg cosine theta is equal to 2mgr minus 2mgh divided by r. We can distribute the r. We can get rid I think I did something wrong on my other sheet where I solved this, but that's okay. We can get rid of the m, we can get rid of the g, because they're in every term. Oh. You know what? I'm actually going to not get rid of the r like that. I just realized what I did in the other one that made it easier. I'm going to multiply each side by r to get rid of the r. And so when I do that, what I'm left with is r times cosine theta, which is equal to 2r minus 2h. Now, neat thing I can do here. R times cosine theta is actually this side length, which, via the Pythagorean theorem, is also square root of r minus h squared. So I can actually replace this with square root of r squared minus h squared. And that's great because that means I don't have that theta floating around, and my only variables are r and h. If I square both sides, what I'll wind up with is r squared minus h squared is equal to 4r squared minus 8rh. Yeah, because 2 times each other. plus 4h squared. Now, to solve, I'm going to have to set up a quadratic or factor. So plus h squared minus r squared plus h squared minus r squared, because I need that to equal to 0 in order to do that. We'll get positive 3r squared minus 8rh minus, plus 5h squared. Thankfully, this is factorable, so I don't have to use the quadratic. If I factor it out, I'll get 3r minus 5h times h plus r. Now this solution equals 0. This solution is that negative r equals h, and that means that it'll fall off when it's under the hill. That's not super relevant, so no physical meaning, and I can ignore it. The other solution, however, does make sense, which is that 0 needs to be equal to 3r minus 5h. If I add 5h to both sides, we'll get 3r equals 5h. Divide each side by 5, divide each side by 5. And when we are at a height of 3/5 of the radius, that'll be our height when this sucker pops off the hill. So, recapping the key points on both of these real quick. When you're going around a loop-de-loop, you have the least force towards the center at the top because it's going the slowest, and you also have the normal force working together with gravity. At the bottom, the normal force works against gravity, and that normal force needs to be much bigger because it is both going faster, so you need more centripetal force, and it needs to fight against gravity to provide that centripetal force. The point at which it starts to slip off of the top, if it does slip off of the top at all, will be the point at which the normal force goes to 0 because it gets pulled in too hard and spirals into a tighter circle. In this case, it was the flip. The point where it falls off is the point where the normal force is 0, because the normal force makes the centripetal force smaller because it pulls away from the center of the circle. When we go too fast, we need more force, and we can't get it because gravity is not pulling in strong enough and normal force can't pull in with it. So at the point where normal force is 0, it slips off because that's the point where it's not pulling in enough. So we use our circles equation, we use our energy equation, and there's some differences based on the radiuses for it being a full circle versus a semicircle, and whether or not it's starting at the top of the circle or above the top of the circle, and otherwise the math is pretty similar. Weird stuff with the geometry here, using the r cosine theta and the Pythagorean theorem together, which doesn't normally come up, which is kind of neat, and plugging into the two equations and solving from there. So, hopefully that was helpful. Goodbye, YouTube.